Yeah, thanks for reminding. Okay, so as I said, this article, this exercise is based on an online article by Sebastian, and this is the original link for the article. You can go through the link. Here I have just used some really interesting snippets from his article because I find these are very insightful from the perspective that if you want to understand the concept of kernel PCA in practice. Okay, so because in the class we have studied from a theoretical perspective, and also I think we have an exercise today where we also do a bit of mathematical manipulation and see that really we do not need to compute the kernel function itself, phi of x, the transformation, but we can just use the idea using Mercer's theorem to actually uh, make use of this kernel trick. Okay, so we will see that from the theoretical point of view today also, like we did in the class. Okay, but before going into that, I want to make things a bit interesting and want to show you how this thing is helping us in practice. Okay, because this gives you more insight and more motivation. So we just import some usual libraries. Okay, so since this article is mainly based on scikit, so he's importing some libraries from the scikit. Okay, and as you can see that we have the p distribution and square form imported exponential functions, and then we have from linear algebra eigen. Okay, and from NMP as NP simply. So first we will go through the mathematical definition of RBF kernel, and we will try to implement that. So the mathematical definition of RBF kernel, okay, is quite simple. It's just that you have xi minus xj, so the input, the two input vectors, okay. So you convert for them element wise, right? And then you have the sigma parameter, which is kind of a hyperparameter, if you would say, and it is like you have to choose the sigma parameter depending on your underlying distribution. So primarily you have to experiment with a lot of sigmas, and then you can uh, find which sigma fits your data distribution well. Okay, so this is kind of a heuristic method. So there's no analytical method for calculating it. It's kind of heuristic. Okay, so actually this is gamma. This is called gamma, but this gamma is actually in turn based on this sigma, which is the, in some sense, you know, mm, the standard deviation, if you think in terms of the exponential functions or Gaussian function, which you allow. But it is a bit tricky. It is a bit different than that. That's why it has a special name, which is RBF kernel. Okay. Okay. So stepwise KPCA. So here what we do is that we implement a kernel PCA, RBF kernel for the PCA, principal component analysis, and then we have this P distribution where we say that calculating the squared Euclidean distance for every pair of points in the m cross n dimensional data set. Okay, so if you know that if you want to go into detail of implementation details, okay, what to expect, what this function expects, you can simply use scipy help. Okay, scikit help, and you can see that it takes in an x nd array, which is a m cross n array of m original observation in an n dimensional space. Okay, and then we have the metric, and the metric we're using is square Euclidean. Okay, I hope this is enough. Okay, so you have a very quite variety of metrics here, which distance metric you want to use. So you could use Chebyshev, you could use Hamming, you could use simple Euclidean, you could use cosine, and you could use square Euclidean, and stuff like that. Okay, so let's not go into detail because I think you guys are smart enough and you can figure it out further. Okay, so we have the square distances in this matrix. Okay, and then we convert the pairwise distance into a symmetric matrix. This is really important. So because we want to have this pairwise distances, but we want to have a symmetric method m cross n so that it because it would be really easy for for calculation purposes, for calculating, as you would see in the next step. Okay, because now you have this matrix of square distances, and you can simply implement this gamma function. Sorry, this kappa function. Basically, this RBF kernel. Okay, because you have simply this squared Euclidean norm, and you can simply multiply this gamma with this gamma multiplication is element wise actually with this matrix. So this kernel is now contains element wise pairwise square distance symmetric matrices for which each element, for example, x1 and x2, and then x1 and x3 and x1 and x4 up to x1 and xn. If we have n observations, if we have m observations, then we have x1 to xm. Okay, I think in this definition we are using m cross n. Yes, so it is the m dimensions of observations. Okay, so we have m observations in an n dimensional space. So guys, I expect that you will, if you don't understand something, you will unmute yourself and interrupt me, because I would really like that, because I don't like to go into chat and see what somebody has typed. Okay, so please use unmute yourself, because we are only 37 guys, so I think this is enough. We could handle it. Okay, so and then we center the matrix, the kernel matrix. Okay, and now we have okay, first we find out the shape. Okay, and then we use this one and we once. So okay, this cute expression, or I mean, I call it cute, you might call it scary, but it's not really scary. We would do that in the exercise, and we will see what's actually happening here. Okay, so it's just centering the symmetric matrix. We will see that in the theoretical exercise. Okay, don't worry about it. So we have something which, so it is basically we calculate in some sense the mean of this K matrix, this kernel matrix. Okay, and then using that kernel matrix, we subtract the mean from this kernel matrix, and then we have this yeah, so this expression just subtracting the mean in some sense, okay, from the kernel. Okay, so there are many ways of doing it. Some could be very mathematically robust, but at the end of the day, this implementation serves also quite well. Okay, yeah, so coming back, so now what we want to do is we want to obtain the eigenvalue decomposition. Okay, so we, and basically this function from SciPy linear algebra, this actually calculates the eigenvalue distribution, and they are in the decreasing order. So the highest eigenvalue is at the first position as at sigma 1, and then you have a decreasing order of eigenvalues. Okay, so with this function you get two outputs in some sense, and yeah, so two return values, you have eigenvalues and you have eigenvectors. Okay, so you could see and go into help and figure out what other things can be done for this. Okay, yeah, so that's pretty cool. So let's just try to run this. I think it's also a good idea. Just click on it so that it's loaded in the inner code collab. Okay, so now very interesting idea. So if you see, this is a toy data set. We call it, some people call it half moon data set. So or two half moons. So as you can see that if this is the class distribution, then linear kernel would have quite difficulty in finding some good separability, because this is like a toy data set, so we have only two dimensions. Okay, so we cannot find in a straightforward manner any linear function which does the job. I mean, you could always find some piecewise linear functions, but that's not what PCA is doing, right? So if we have a simple non-linear 2D data set, then the linear PCA or the conventional PCA which we have studied so far fails. Okay, so we have to come up with some kind of the kernel PCA. We have to find some interesting kernels which could enhance or boost or kernel using kernel methods the PCA. Okay, so this is a Twitter set. Okay, guys, are you following me? Please unmute yourself or just say in the chat yes, yes, yes. because it's very weird. Thank you. Ah, yeah, thanks. Okay, so coming back. So now we simply have matplotlib line right, and we import pyplot, splt, blah blah. Okay, and then this make moves dataset is already in the scikit-learn library. Okay, so we just say make moves. Okay, we import this function, and then we tell them the number of samples. Number of samples is a point, so we have like roughly 50 points as blue and 50 points as red. Okay, and this is just random initializer, so this is not really interesting. You could set it to to any number, any integer. It would not be much of a problem. Okay, so then we define a plot, blah blah, and then we say okay, we have this alpha 0.5, and we have the color red and the color blue. Okay, for y, if y is 0, right? I mean, because make moves gives us two classes, okay, 0 and 1, right, which are here. Okay, so yeah, we just run it and then we show. Let's see how does the plot looks like. I mean, you could also randomly generate more samples. It would run the same. It's just that you would not see the individual samples now because there are so many samples in this 2D space. Okay. Yeah. So let's just keep things simple, and we have 50 samples, let's say, and now you see they are more or less equally distributed. Okay. So just as a I mean, intuitively we can see that it would the linear PCA would not work. But let's just say, for the sake of argument, why not try it? Okay, why not try it and see whether it really works or not? Because one thing in theory and one, I mean, the purpose of the exercise is to provide you with some empirical evidence so that you rely on what we say in theory. Okay, so it is some empirical evidence to support your belief in the to support your understanding of the theory of the kernel PCA, of the kernel methods. Okay, so linear PCA. So I mean, this is just a comment. The since two half moon shapes are linearly inseparable, we can see that we cannot find a linear line which separates them. Okay, we expect that the classic PCA will fail to give us a good representation of the data in 1D space. Here we will use the PCA class that is implemented in scikit-learn to optimize to perform the dimensionality reduction. Okay, so we'll simply import the PCA from the scikit-learn library. Okay, and then we say okay, we want two components. Okay, because we want to see what's happening or what could actually this linear PCA do. Even we are actually not performing any dimensionality reduction because it's only a 2D data set. Okay, so there's no dimensional reduction happening, but still we would just want to see because it's a toy example. So we keep the maximum number of principal components, which is 2, and then we try to see what's happening. So here we try to fit transform this x, which we which is actually the data make moves. Okay, this thing which you are seeing here. Okay, and then we try to fit transform this, uh, and now after fit transforming it, now we have the two principal components again, like with 0 and 1 label, right? So we want to plot them and see what's happening. So as you can see that, okay, let's just try to run it again. So as you can see that it has simply inverted this thing. So you might see that there's nothing happening here. You could argue that, but there's something happening here. The first two principal components are doing something. You can see, for example, in the coordinate sense, it is coming from -1 to 2, and it is coming from minus 0.5 to 1, right? The data range, but here the data range is a bit different, right? So it's doing something, but it's not able to find any good solution because linear PCA cannot do it. So we have, like, in some sense, shown it, but still, okay. Uh, Maybe we could try something else. Okay, let's try to see and plot first principal component, right? And see what's happening there. So if we plot the first principal component, then we see that the data is not linearly separable in any way. You cannot draw a line here, right? Because the classes, the blue and red, the two classes are intermingled with each other. They are like on top of each other. So you could not possibly separate them. So I hope you guys are following this. Say yes, or if you have any questions, please unmute yourself. Okay, only Julian is saying yes. Moritz. Moritz is my favorite guy now. He always responds. Okay, so okay, now let's go back to this Gaussian RBF kernel. You know, it's coming from the same family, right? So now we will perform dimension reduction via RBF kernel PC on our half moon data set. Okay, so the choice of sigma depends, or choice of in this case gamma depends on the data set and can be obtained via hyperparameter tuning techniques like grid search, blah blah. I mean, hyperparameter tuning is a broad topic in itself. We don't want to go into too much detail there. Yeah. So, but still, the gamma, as I told you, could be found via hyperparameter tuning. Okay. So we are just fixing this gamma to 15, right? And the components to 2 and see what's happening, right? And yeah, let's just do it. So as you can see that somehow beautifully, this Gaussian kernel or Gaussian RBF kernel was able to do something, right? So we see that they are like separated in a beautiful way. So you could see that, okay, well, if somehow, if the PC1 value is greater than 0, right, then I have my separate classes, right? That's pretty cool, right? So, okay, let's just see what's happening here, right? So now we plot the first principal component. Okay, I think I just, what you can say, change that X. So let's just keep the dimension same. Okay, so okay, so now you can see that, like I told you, if the PC1 is greater than 0, then we have a beautiful class separation. So now the data is linearly separable. I find it pretty cool. So yeah, with a simple two example, we can see the effect of this RBF kernel. Now let's try to see what's happening with here with this gamma. Okay, just play around. So let's say we make it too high. We make it to 1000, right? So you can see that what's happening here is actually trying to skew the distribution, right? So if you see this red here, so the top thing, right? The top half moon, so it is skewed, it's pinched a lot, and whereas this uh, the blue circle, the blue half moon is not pinched. So it's some effect of this gamma happening here. So yeah, I mean, I do not want to go that why this is happening. I think it's very intuitive, and you guys could figure it out. I mean, there must be something which should be left to students, you know. So let's say, okay, now we're going to extreme of gamma is equal to 1. Let's see what's happening there. Okay, now you can see that the data, I mean, the RBF kernel is trying to do something, right? But it's not able to, what you can say, distinguish very well. So you see that there's an overlap between the blue and the red class, right? I mean, also if you see in the first group principal component, there will be still some overlapping happening here, right? You can see that. So it means that this gamma has a very important role to play. Okay, so this gamma is really important. That's why we say the hyperparameter tuning plays a big role. And yeah, so you should know what is the right range for your algorithm to perform well, right? So for example, if you, I mean, in my opinion, if you have something like 10 or greater than 10, so this thing would work very well. I mean, this RBF kernel for this two half moon set, right? But you have, I mean, so this is the range, so you should not go less than 10, because if you see for exactly 10, there is a swap of one only, right? So probably, so this is kind of grid search. We're trying to do a grid search. What's the best? What's the minimum? So 11 is also not fine. So can we say, okay, let's say 13. Oh, sorry. Oh, 131. Yeah, so 13 is kind of the right gamma. I mean, if you increase it, then it will still it will still work like we showed for 1000, 10,000 gamma. Okay, so enough playing around. So now just a comment that we can clearly see that the projection with RBF kernel PCA yielded a subspace where the classes are separated well. Okay, so such a subspace can then be used for linear classification models such as sport vector machines or naive Bayes classifiers, because you need because in practice what you need is that you have a lot of plenty of data, because remember PCA is not doing classification. And PCA itself is just a dimensionality reduction technique. Okay, so it's an unsupervised method. So this blue and this red color is because we have the insight into the data, and we know, because we created this data set, we know that this is how it's supposed to look like. This is class 0 and this is class 1, or this is class red or this is class blue. But it's not like PCA is interested in that, because PCA doesn't know the labels, and it's not working on the labels itself. So it's just that you want to reduce the dimensionality. So for example, if you have n dimensional space, you want to go to a k dimensional space, right? And then in this k dimensional space, you want to then apply your classification model, which can be a sport vector machine, which can be a neural network, which can be anything, right? You don't want to deal in very high dimensions, because you want to be efficient, because there's sometimes a lot of noise in the features, and we know all the motivation for that in the dimensionality reduction. I think we have covered that pretty well. Okay, so now this guy is doing the same thing with the built-in function of kernel PCA, right? Of sklearn, right? So the same thing is happening there. Okay, now we're coming to something like a different data set. I mean, is it something which is happening on this only half moon data sets? But there are like plenty of data sets like that in practice, right? So this is, I think, one of the data sets which we already discussed in class. It was concentric circles, right? So again, we use scikit-learn data set and make circles, blah blah, random sample 1000. So the noise is how much noise do you want in the circles. If you have zero noise, then they would be like perfectly centered there, right? But you put in a little bit noise so that we see the variation, and we try to emulate the real world scenario, right? Okay, so yeah, these are all the parameters for this make circles. If you're interested, you can go to help and see what's every parameter is doing. I mean, we could also see some effect of the noise, but it's pretty clear. Okay, so yeah, just let's run it. Okay, so we have again two beautiful classes. Okay, and now we run it. I hear a noise, so there's some question. I'm happy. Who wants to ask? There's no question. Okay. I'm not happy now. Okay, no worries. So again, so now when we run this, so you can see that there is a bit, in some sense, overlap happening here, right? So this gamma with gamma is equal to 15, right? So, but there's one interesting thing happening. If I zoom in, then you can see that there is some overlap, but this is the overlap for, let's say, for for PC1, right? And if we go here, okay, just I think there was a mistake in labeling this. Sorry. So this was from the linear PCA. Okay. I was worried why this is overlapping happening. So if you use a linear PCA, then actually there is an overlap. Okay, so linear PCA will not be able to distinguish between two classes, the red class and the blue class. Okay, I mean between these two clusters. Okay, so and then if you use this RBF kernel, then you can see that they are really well separated. Okay, and again, if you play with this gamma, they might overlap and they might not overlap. So this effect you have to see. But gamma is equal to 15 is a good choice, and you play it with it, and you are in a very nice Xusheng. Yeah, Xusheng. So this is this overlap is because it is coming from the linear PCA. So the linear PCA is not able uh, to separate this data, right? So the linear PCA is trying to collapse this whole variation, okay, and trying to measure the variation. Okay, so as you can see that, for example, uh, I mean this is a perfectly symmetric data set, so you can see that in both directions the variation in the red dots is more, right, and the variation in the blue dots is less. So this can be seen here. So the first for the first principal component, the variation in the blue dot is from minus 0.5 to 0.5, whereas the variation in the red is from 1 minus 1 to 1, roughly speaking. Okay, so this is what the linear PCA is capturing. It's not able to transform it into a new space and calculate principal components there. So when you hear the word kernel PCAs, or whenever you hear the word kernel, you should think that now we were living in a space, let's say, uh, in some space. Okay, let's call it, I don't know, H. Okay, and after the transformation, the kernel is actually providing you a transformation. So now you go from this H space to a new space H star. Okay, where this after transforming your data, and then in that big space, you can see that you are very well able to linearly make the data linearly separable. Okay, in that big space H star. Okay, or let's say in that transformed space, not let's not call it big space. Okay, so in that transformed space, and then after performing your analysis there, you then come back to your original space. Okay, but with the kernel trick and with Mercer's theorem, we actually don't need to perform that transformation. I mean, we don't need to know that transformation function, which we'll also show shortly in the theory exercise. Okay, but it's very good to have mathematical basis and understanding of these topics, so that we know that if the kernel satisfies some basic conditions, then we are guaranteed to have we are guaranteed to have we have a mathematical guarantee or surety that there would be a solution in that space, and we would be happy, right, from that perspective. Okay, so this inner product would be valid, and we could use all the theoretical guarantees there, right? Okay, so yeah, but this is what we are seeing here in practice, that what's happening or not. So I think Yuzhang, did you get my yeah, thanks, you're welcome. So this is after linear PC, and now we are here in the RBF kernel. Okay, so with that I would try to take 5 minutes break. Okay, and we come back after. Okay, so great. Now I'm going to share some. Yeah. So now let's. This is a very interesting idea in machine learning, because I also want you to understand this, that there are some problems with the data, and then you try to come up with a solution. But the solution you come up with is not always a very universal solution, you know. So for example, we come up with this kernel RBF for this kind of data set where we cannot linearly separate, where linear PCA fails. But now let's just see some instances where the RBF kernel fails, you know. So let's just see it. So then we come up with more solutions and more solutions. So it's like an ongoing process. Okay. So this is, uh, I mean, one of my favorite examples. It's called Swiss roll example. I don't know whether you guys know Swiss roll. So how many of you guys know Swiss roll? Can you please tell me in the chat? Because I want to see that you guys are listening to me. I mean, I will show you. Okay, don't worry. We have got Google, and we are on the. Yeah, it sounds delicious. Yeah, I mean it's very very what you can say sweety, very sweet. So not for everybody, but yeah, but I like it. So they're like different flavors of it. But I mean the point is not the. I mean we're not talking here about the dish Swiss roll, but I just want to see you. I mean there's one very beautiful pattern here, which is this pattern. You know. So yeah, you see there is one what you can say one pattern one this what is called let's say chocolate pattern, okay, and one this is white pattern, vanilla pattern, right? And you can also see this pattern here and here and here and here. So it's like their trademark, okay. Moritz, you want some? Yes, you might get some. um, Probably I think they are available in Edeka or some bakeries. Yeah, okay. So but this is where normal people see Swiss roll, they think about that. But we are engineers and we are computer scientists, so we don't see Swiss roll like this. For us, Swiss roll is like this. I hope you can see it. So now just try to imagine this is the Swiss roll, okay? Which so you might, I mean, you don't want to eat this, right? So this is a Swiss roll in 3D because we were talking about all the data sets in the 2D, and now we just want to go to more complicated data structure, which is a Swiss roll, and it is in 3D. So definitely, uh, I hope you could figure this out. That this is a Swiss roll. So believe me, this thing for engineers. Okay. Yeah. So very nice Swiss roll. So now, if we want to do it with simple linear PCA, and we want to see two principal components, you can see that this is how the two principal components are aligned. So you know there's like this very nice swirl happening here, but we cannot possibly separate it, right? We have no clue what's happening underneath for with this data set. I mean, the linear PC has tried to capture something, you know, it is able to try. I mean, there's not very much intermingling happening, but still, it's not separable, all the classes, okay? So if you see in terms of the first principal component, you can see that everything is overlapped, okay? So we have no clue what's happening underneath. So good luck with this. Okay, maybe the RBF kernel can help us. Let's see. So we go to the RBF kernel and we choose gamma is equal to 0.1. Don't argue about the gamma value. We can try to change it and then let's see what would happen there. Okay. So we see gamma is equal to 0.1, right? And yeah, so it tries to do something again. I mean, it's not like the kernel would fail completely. I mean, it would try to capture some essence of the data, but not complete good picture, the nice picture we were having previously, right? So now we want to plot the first principal component, and we see that our RBF kernel has failed. Uh, that's really bad. That's really bad, right? So we didn't want it to fail. I mean, you might say that, well, it's maybe because of this gamma is equal to 0.1. If you choose the golden value of gamma 15, which always seem to work, it might work. Let's see. With gamma is equal to 15, okay, let's then also change the legend. Okay, I'm not going to change the legend. I'm just saying plus 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 because we are going to try different gamma values. Okay, so you can see that something is happening here, right? But we are not sure what's happening. So let's just go and see the first principal component and how good the distribution of the classes is there. So as you can see that with the first principal component, all the classes are in some sense gathered here. You know, so it has pushed all the values to the zero. You know, so it has a very stark effect. So I mean, if you want to see this effect in extremes, let's just put gamma is equal to 1000 and see what's happening there. So now you see that a similar phenomena is happening there. The gamma values are in some sense, okay, now we have only two extremes. So one point is here, one point is here. So all these different data points, they're all forced to choose one block. But this is not what Swiss roll, I mean, this is not giving us any information in the Swiss roll class itself, right? So maybe if you go like 0.001, maybe this would help. Okay, if you go to very low dimensions. But you see, if you go to very low dimensions, then it's the same as a linear PCA, because you have chosen such a low gamma, and in fact, as gamma approaches to zero, we can show that what's happening to this PCA function, and yeah, if gamma approaches to zero, it means the sigma is approaching to infinity. Yeah, so if gamma is approaching to zero, then if we go to the original function for RBF, yeah. So you can see that if this goes to zero, right, then we have exponent of zero, which is one. So this value will always be one, right? No matter what is the difference between these two. So yeah, so gamma approaching to zero is not a very wise choice. Okay, so yeah, so now RBF kernel fails, but are there any methods where which we can utilize to actually solve this our Swiss roll problem? So the answer is yes, we can do that. The Swiss roll problem is solvable, but we need something which are not, I mean, which are out of scope for this lecture, right? So I encourage you to go to see this local neighbor embeddings, right? So some people call them LLEs, like locally linear embeddings, right? They are able to solve this issue, and they to some extent, right? And then there are like many more methods in this sense. Uh, linear embedding is a one method. Then you could also use some very fancy deep neural networks to solve this issue. Okay, yeah. So that's pretty much it. So do you have any questions? Because now we will go to the theory mode. Yeah, it was fun. Okay, so let's just start the theory. Okay, before we go to the theory, I just want to. I mean, we have already what you can say. We have already seen the solutions. Okay, and but I mean the solution of the assignments. But there were some comments and some memes which I want to show you, which were really amusing. Okay, yeah, and which kind of told me what's happening with the students, right? What students are doing, and you could see this in almost every project. Okay, so I would just try to share my new screen. Oh, okay. So I hope you guys are. Please say yes if you are able to see this in the chat.
Yes.
Yes, great. So every group project, if you have watched this movie Hangover, then you could easily relate it. So this guy does 99% of the work. He has no idea what's going on the whole time, and he's disappearing at the very beginning and doesn't show up again until the very end. So I think this is true of every assignment. But there's also a very interesting thing in some assignment, not all the groups, but in some groups, we could see this kind of behavior happening. So you make half the assignment and I'll make the other half and then we will join them together. So there are some tasks which are very nicely done, by the students, and then there are some tasks which, I mean, it doesn't seem that all the group members have really discussed those tasks. So I would encourage that for the assignment 3, please try to discuss with each other as much as possible so that your assignment at the end doesn't look like this. Okay, because you all get one grade for the assignment. Okay, yeah. So and then there were some students who were complaining about this behavior. So I really like this idea. So the story of every group project. I mean, this guy is driving on a motorbike, and I mean, this guy doesn't have like the gasoline, the petrol, or the fuel. So he's just he's just he's just tagging along. So, but this guy is not even there. Okay, so please don't be this third guy because there were some emails coming in that the group members are not uh, responding well and blah blah blah. So we I really wanted to show this meme in the beginning of the class so that you guys please don't be this third guy. At least be the second guy. If you're not doing all the work, but please be you know at least tag along. Be there. You know what's happening. So yeah, and then finally the fourth one. I don't want this to happen. So what group projects are supposed to teach you? I mean, primarily teamwork, and then collaboration and responsibility, which is very important, and also communication. But what group projects taught me is trust no one, and all other things are very low. So please, for the assignment number 3, I want that you guys work really as a team, and if some members don't understand things, then help them out. Yeah. So that's like the spirit of the assignment. Okay. So let's just go to. I'm going to because now I'm going to write on the tab. So I think I should close my video because yeah, then I would be like looking down, and then you would be wondering where he's looking. Okay. So yeah. So okay, where was the kernel PCA theory? Okay. How much time we have left? Yeah, we have plenty of time. We have plenty of time. Great. So I think we can do it. So now coming to this awesome theory. Uh, so we have kernel. We have kernel. Please unmute yourself if you do if you have to ask the questions because now I will not be looking at the chat at all. Okay. Okay. So now I want to choose some other color. Okay, let's say blue, right? So the task we have only one task today. Okay. So we say that there's a 5 function, right? I want to be as close to the notation in the lecture as possible. And all of this thing will be uploaded on the Moodle, don't worry. we have from RP to RQ, right? And then, I mean, this is a vector which is mapping from, I mean, what is this called? Okay, let's just use. So this is called the observation space. I mean, where you have observed the matrix X, right? And we call this to, I mean, we can call it feature space, okay? Yeah, I mean, the transform space actually, but let's call it the feature space, okay? And when, I mean, when this is applied to matrices, so this phi, it operates column wise. Okay. I mean, this is just for the notation so that you understand what this phi is doing, right? This is just some definition when applied to matrices. I hope you can see that. Okay. So the respective kernel, we call it kappa. I hope I will try to exaggerate this kappa with this like this. Okay, so the kappa would be that from RP cross RP, it goes to a number R, right? I mean, in other words, if we have X and Y vectors, right? So we have this phi of X, that Y function, right? And this phi of Y. Okay, so this is just a formal definition. Nothing interesting happening here. Okay, so yeah, so then we have task A, which is that let X, the observation matrix, right, belongs to RP cross N. This is our training matrix, right? Okay, cool. So now we want, I mean, the task is to find out, find an expression, right? Yeah, go ahead. I think you can unmute yourself. Shuangzhong. I don't know how to pronounce your name correctly, please. Go ahead. You cannot unmute yourself. Allow participants to unmute themselves. Yes, you can unmute yourself. Please go ahead. Okay, maybe it was by mistake. I do not. I do not.
Sorry, I just wondering which part are you talking about? Are you talking about assignment 3?
I mean the memes I was talking.
Or just talking about this theory?
Okay. Okay. Yeah, this is about the lab 7 theory. Okay.
Okay, thank you.
Okay, so what we want to do is that we want to find an expression for centered, like we use this centered phi x. Okay, so let's just try to do it. So we know that if you remember that phi of x minus 1 by n phi of x, we have covered this in the lecture. I think, yes, I think we did that. We were talking about the H matrix, right? But you will see that shortly. So if we want to, so this is actually the mean of phi of x. So if you subtract the mean of the phi of x, then it's centered, right? I mean, that's the definition actually. That's how we define centered, okay? So then we have phi of x common, and then we see the, okay, identity minus 1 by n I of 1 of n. So this is one matrix, right? I hope you follow the notation from the lecture. Okay, so that's it. So now we have an expression, and this whole thing, the bracket, we call this thing H matrix. So if we want to center phi of x, we just multiply it with H. Then we get a centered phi of x. Okay, yeah, that's pretty simple. Task one done. I mean, we are doing all these tasks and they will be quite simple, but we will then glue them together and show why they were important. You know, you might see that there's no, I mean, what's the rationale for finding this phi of x, you know, but it's just that you should know that if you multiply h with phi of x, you would center it. Okay, so that's the take home message. Okay, so now the second task is that we want to find out, we want to find out uk, okay, or we want to express uk in terms of phi of x, h, uh, and let's say v, okay, and sigma. The sigma is from the eigenvalue decomposition, right? So we want to see that can we do that? So this is what we want to find out. Again, this is a smart part of the puzzle. Then we will glue all these pieces together, right? Okay, so let's just try to do it. So solution. Okay, we know that from the lecture. I think we have already covered that in the lecture. That k is equal to phi of x, right? We already know that. And this is called Gram matrix. This is different from the kappa, right? This is a Gram matrix. I'm just writing it down so that you guys don't confuse it with the kappa. Okay, so this is Gram matrix. Yeah. So, and then we know, I mean, and we also know from the lecture that if we want to center this matrix, let's say centered Gram matrix, I noted by tilde. Let's just try this. Centered Gram matrix. Right. So centered Gram matrix is given by h into k into h. I mean, if you don't remember this, then you could look up in the lecture notes, and we showed that how. I mean, if you want to simply center the phi of x, then you have to multiply it from the right only. But if you want to center uh, k, then you have to multiply left and right both sides with h. I mean, let's just quickly see how, I mean, you would really understand it, that yeah, it's really, really simple. So I mean, I'm just going to write it down without any further ado. So you can see that this is also equal to phi of x into h transpose phi of x H. Any questions here, please? I mean, I'm simply, okay. And what I'm doing is that, uh, I mean, K tilde could also be written as phi of tilde transpose into phi of tilde, right? I mean, it's just one and the same thing. It's just another way of writing it, okay? If you have questions, please interrupt me. Otherwise, I'm assuming that I'm good to go. Okay, good. Okay, so let's just also define, just for the notational sake, that K tilde is equal to V sigma V transpose, which is eigenvalue decomposition, right? We already know that. Okay, and then I'm just writing so that you all are on the same page. Yk means first k columns of V. Okay, V matrix. And similarly, UK also means of U, right? Where V and U are belonging to, are okay. I think let's not confuse you guys. You already know from the notation what would they belong to. Okay, right. So now I'm going to write an expression that we also know that if you want to have an SVD of K, right? Right, we could write it like this, okay? And similarly, as we have already seen that K tilde is equal to, so this implies that okay. So let's just see now if we can. I mean, there is a little bit of mathematical step here, which I don't want to go into detail, and I think this is pretty straightforward because we are running short of time and I have another task to do. Okay. So now I'm just uh, leaving it up to you guys as a homework assignment or your personal understanding. Okay. So I'm just going to write down the next step, what could happen. Okay. So U sigma. Now I am transferring from the SVD to EVD expression. So I'm just using half. Okay. V transpose. This must be equal to phi of X into H, right? And then what we are going to do again is that we're simply, okay, let's just go a bit faster. Phi of X, H, VK. So there's this K happening here, right? I'm just skipping some steps. So you could see that, okay, if we are just interested in, oh, sorry, we are just interested in first K columns, then We are simply doing just that. Okay. And then this further implies that UK equal to phi of x h vk sigma k half inverse. Okay. Minus. Okay. So this is what we wanted to do. We wanted to find out an expression of UK in terms of all these matrices. Okay. Now we are going to task C, which is we want to express. Okay, let's just express kernel PCA scores, which are called SK. Okay. Okay. So we have to find an expression for SK, for kernel PCA scores, right? And the second thing which we need to do is we need to see that we can compute them. We can compute when kappa is known, right? Kappa is known, kernel is known, and phi function is not known. So this is what we said that this is what we should be able to do. Then when kappa is known and phi is not known, right? Okay, so let's just say that for the purpose of task, we are interested in finding this SK for test data set, right? Y, right? And I'm just writing that Y is it belongs to P cross N, and just to differentiate it from the training, I'm calling it NT, right? But it's just for the notation so that you don't get confused with the notation. But it doesn't matter that much at the end. Okay. So again, for first we want to try to center the 5y, right? What we want to do is that we have this 5y and we multiply it with h. We have the centered y, right? But there's very interesting thing happening here. This in this h. This is not h. This is a little bit of h prime. I think it's even better if we don't use the notation a. Okay, we just want to see, okay, what is this? Let's just open it up because otherwise you would get confused. So phi tilde y, we want to center it. But the question is, if at the test time we don't know all the samples, if there are new things coming up, then do we want to, or we have trained a classifier model with the data, right? So what mean would we use? Would we use the mean of the test set, or would we use the mean of the training set? So it's always a good uh, practice that you use the mean of the training set. This is really, really important point from the practical point of view. So you don't subtract the mean of the test set, but the mean of the training set, because that's how your classifier is trained, right? For PCA, it would not matter that much, right? But for the classifier, it would matter a lot. So that's why you need to be consistent. So that's why this mean is the mean of the training set, not the mean of the test set. So I'm now going to write 1 So that's why I'm using phi of x here, not phi of y. This is really, really important. And here I'm using NT just to match the dimensions, right? Because otherwise the dimensions won't match if you use the same N here. Okay, I hope this point is clear to you guys. Okay, so now moving on, we want to now find out the scores. As we know from the PCA, this is already known, right? SK is equal to UK transpose phi y. If you go into the lecture notes, you would find this formula for the scores. I'm not going to motivate it for you guys. Okay, so this is equal to, maybe I should write it, lecture notes. Okay, because they calculated this in detail. That's how scores are defined. So then we simply use this UK. I'm just going to go back so that you see what I'm talking about. Uh, yeah. So now I'm going to use this expression, right? This whole expression, this one, because I was, yeah. So I'm now going to use this expression and put it there for the UK. So that's what I was saying, that now you will see that how the pieces of the puzzle match together. Okay. Sigma X transpose, and then we have sigma tilde Y, right? So this whole was coming from, okay, this thing is just this, right? And then we have sigma Y. We have not opened sigma Y. And now if you open sigma Y, right? And then if you do the manipulation, just do the simple multiplication, then you have this multiplied by VK transpose into H, and then you have kappa, right? X comma Y minus 1 by N K into 1 N into 1 and T transpose. Yeah, so okay, just one comment. I mean, I'm not going in detail into how we are calculating this thing, right? But if you simply put this thing into this and use the definitions which we have defined here of the phi, right? And if you use all these definitions, then you can easily simplify these terms and come up with this expression. Okay, right. So now if you see this expression, okay, let me just copy this expression. I don't know how can I copy it. Okay, I think I cannot copy it. Okay, if I simply use that expression here, right, this expression, so you can see that there is no phi involved here, right, which was the purpose of this exercise, that you could calculate when phi is not known. So in this whole expression, the phi has vanished. Only the kappa has remained. Right? So that's why we say in practice that we do not need to know the exact transformation function phi in order to calculate or solve the kernel PCA scores. Okay. And just for the sake of simplicity, so that you guys have a sanity check for this method, if we say that if x is equal to y, I mean, if we are interested in scores of training set, then we can simply put x is equal to y, right? And then if we solve this in this scenario, right? So here then we have kappa x comma x, right? And then let me just write it down quickly. Half vk, okay. And then you have h, and then you have, I'm just writing down the expression again and again so that you guys understand it. Minus 1 by n k 1 n 1 n transpose, right? And then you have, I mean, this is again, you can easily simplify this thing. I hope you guys can do it, right? So vk transpose hkh, right? And if you simplify this further, it would become something like sigma k half into vk transpose. So again, for this, you don't need phi. Okay, so that's job done. So now we have only 1 minute remaining, and the task for today is done. So do you have any questions? So please unmute yourself. Like I told you, you can always interrupt me because when I'm
Hi,
writing down, I not see on the chat.
hi. I have a question about the kappa.
Yes, please.
So the kappa is defined from RP cross RP into R, and
Yeah.
the
Let me just go there.
are matrices, right?
What?
So in the last expression you have written the XR matrices, right? The arguments. If you can go to the last page.
Yeah. I mean, you can just see it here. Okay. So this X
Okay.
is RP cross N, right?
Yes.
And when I defined phi at the very beginning, I said that phi, it operates column wise when applied to matrices. Okay.
Yes.
So phi, if you apply it to matrix, then it would convert each column from p-dimensional space to a q-dimensional space.
Yes.
Yeah. So does that answer your question or not?
So can you go back to the kappa function?
Kappa function here?
Yes, so if I put in two matrices, then the output is a vector or a matrix?
Okay, so from the definition of the kernel function, what is it? I mean, you have to think in terms, let's say, keep things simple. Think in terms of a linear function,
Okay.
linear kernel, okay? What is linear kernel doing? Linear kernel is doing a dot product in the Euclidean space, okay? So you have x transpose y, and then you have a single number, right? So that's what this kappa is doing. So it's taking p cross rp cross rp and giving you a single number, right? And if you just imagine more complex spaces and infinitely dimensional space, then there's still this whole thing would hold up. So for kappa, we have a single number coming out of this dot product in that Hilbert space. Okay. Yeah.
Oh, Okay, yeah, I think, yeah, it should be a matrix, right? Matrix coming out.
Coming out of what?
Out of kappa, if I put in x and x, for example, of dimensions q n times.
You mean phi of x? You mean phi of x, right?
Yes, but if phi of x is a matrix and I'm multiplying with another matrix,
Yes.
and if the dimension, then I should get a matrix too, right?
Yeah, if phi of x is a matrix and then you multiply it with a matrix, then you get a matrix, right? But the problem
Yeah,
is not
okay.
that. That is
Okay.
not the issue there. The main issue is that when you have phi of x into h, right, then you are again getting a centered matrix. It's as simple as that.
Okay.
That's what we defined. I don't know. Yeah, so this phi of x into h, if you see here, it's just the same matrix with the exactly same dimensions. It's just centered. The mean is subtracted.
Okay. Yeah.
Yeah.
Okay.
And k, the gram matrix is also a matrix. Let me just show you.
Yeah. Okay.
So this gram is again a matrix. It's phi x transpose phi x.
Okay, I was just confused in the beginning because I think we defined the gram matrix as the matrix with the kappas as entries, and then you generalize the kappa function then by saying that we just applied column wise. So I was just confused with the notation.
Yeah. So
but
that's
thank
why
you.
I took time to define the notation.
Okay.
Yeah, but
Thank
good
you.
question. Yeah. Okay, any other question? Okay, we are already, I think, 5 minutes up. So take care, and I hope you enjoyed the memes, and you will work on the lessons from the memes, and basically try to do not repeat the same mistakes in assignment number 3. So best of luck. Bye bye.